So, yeah, we have been doing proof systems, and we saw the three different systems so far: the Hilbert-style system, the natural reduction system, and the sequence calculus. And they all represent different viewpoints towards proof. And today I'm going to introduce a fourth, and this is resolution. And I call this computer science for mathematical logic, because after all, the course is titled Mathematical Logic for Computer Science. So much of the course, what we are doing is to present mathematical logic as of presumably use in computer science. But today's thing is very different. It's really the computer science guys looking at problems. So how do computer science people look at proofs? Not necessarily Gentzen or Hilbert. They're all mathematicians, and their way of looking at proofs is rather different. So first, the recap, the reduction of the story so far, and then these kind of machine-oriented proof systems. And if I have time, I'll end with first order resolution. So far, we've been talking about proof systems for propositional logic. Of course, as I said, we want to upgrade the whole thing to quantifiers. But since I'm introducing resolution, I might as well talk about that as well. Okay. So, in Hilbert-style system, the main idea is you're not really interested in proofs themselves. You are interested in provability, right? If you remember, I introduced that whole singleton style, the reduction relation, as an alternative to the logical consequence. The main thing is, the thing of interest is the logical consequence relation, the semantic relation, and since that is an infinitary object, you come up with an alternative which is finitary, and then show that they are the same. And the slogan is to truth through proof. Now, for a model theorist, like Hilbert is completeness theorem, once the completeness theorem is established, it's very awkward. I'm very sorry about that. Basically, these two relations are the same. The two relations are equal. Now, in fact, if you read model theorists like Todorcevich or anything like he says, okay, now we can simply forget about deduction. Right? We know that all the work can be done with models, knowing that whenever needed, you can always replace by finite deductions. The real interest is working with the semantic, the left-hand side. Semantic consequence relation. We know that you can always replace it with reductions. We won't actually bother with reductions. We'll work with models, classes of models, definability, etc. So this is typically how the model theories work. And that's, if you remember, the spirit of the Hilbert's program. Right in the beginning, that I pointed out, you have theories, that is a gamma on the left-hand side, and mathematical statements you make in those theories. You want to see that they are true in these theories. All models of that class satisfy. Write down some particular axioms. Look at all models that make those axioms true. You want to ensure that in that class, the statement is true. So, and that carries a lot of problematic infinitary features. You show that it can always be replaced in principle by the finitary deduction process, and after that you can get back into that. This is the Hilbert's program. So in this view of looking at proofs, existence of proofs is the most important. The fact that a statement is provable is important. The actual proof is much less important. You understand the attitude of one way of looking at this. And then you have Gentzen-style proof systems, where I presented natural reduction and sequence calculus. Here, the emphasis is on the nature of proof. The proof is goal-directed and has structure. Right? So you look at the inference rules are very serious. You look at below the line. This is what you want to prove. If you want to establish this, you should have established this thing above the line. And then go down, construct proofs. So the idea is constructing proofs is important. And if you, last time I talked about the sequent calculus, how do you prove consistency? By cut elimination. Because you show that empty sequent represents contradictions. And if you want to show that there is no inconsistency, that means you will never get a contradiction. You just have to show that the empty sequence is never verifiable. And then you argue that the logical rules, structural rules are such that they will never get you to the sequence. So it's only the cut can cause you to lead you to the empty sequence. If you can prove a cut elimination theorem, which means that given any proof, there exists a cut-free proof. Same form. So that gives a proof of consistency of the system. This is entirely self-contained, proved by proof transformation. You show that I can transform proofs to cut-free proofs, thereby I prove consistency. There is no reference to semantics and knowledge. This is the other extreme. Right? So in the Hilbert-style thing, it's all about models. Proofs are things that assure you that you can always replace things by deductions. In Gentzen-style thing, proofs are the most important. Right? Semantics is something that we don't take care of. And for a proof theorist, showing that equality, right, the semantic consequence and the deductive consequence is the same, is a signal that you can forget about problematic notions like truth. What's truth? It's very philosophical. Forget about it and work only with mechanical notions like deduction. So these are two very, very different viewpoints, and both of it is in the mathematical logic. Largely the viewpoint of the model theorist. Now, one question we have not bothered with is how good are these proof systems? And why should we ask this? Isn't completeness good enough? We prove completeness. Right? Completeness says that everything that's a semantic consequence is derived. Soundness is everything that's derived is actually correct and complete. So, is there a notion of good which is separate from completeness? Well, for a proof theorist, you might ask, what about, isn't consistency good enough? After all, I've proved that the system is consistent. That's good enough. Right? Well, but there are other criteria. Right? How easy is it to find proofs? Like I said, in the case of the Hilbert system, finding proofs is very difficult. Right? You take tautology, even if you know it's a tautology, to actually find a proof in the Hilbert system can be very but then you can ask, easy for whom? Right? What is easy for you may be hard for me, and what is, after all, that's creativity. Well, then, another way of looking at it is, okay, what is the size of the shortest proof? For any formula alpha, probably there are many, many different proofs. If it's provable, there are many different proofs. Can we say, looking at alpha, right, looking at the formula, can I say that this formula will have short proofs? This formula must have long proofs. Say something like that. So, and this is a computer science way of thinking. And very brash. Who cares about models or human understanding? The question is how easy it is for a machine to do that. Right? I want a machine to try out the proofs. Will the machine require many resources? Can it do it efficiently? Can it do it time? So, what is the time complexity? So, these are ways of looking at this. And note that if you ask this kind of a question, it's not clear at all whether the model theorist view also may not answer this, nor the proof theorist way may also not answer. Well, proof theory, there is some hope because there is some structure in the rules, so maybe you can find. But in general, looking at a formula, even if somebody comes and tells you it's a valid formula, it's a tautology, how easy it is for a machine to find it. Now, this is of great importance for especially complexity theory, where you are worried about complexity classes, notions like polynomial time, NP, etc., etc. It's all tied to that. But basically, the question is, you are interested in notions like efficiency of the system. Then there are even further notions. So, and that's why I want to move over to today. I'm not going to spend much time on this course, but at least pay for it, where the proof systems that we look at are really machine-oriented. They're not intended for human beings to do. So, human beings love particular kind of structure, like sequent calculus or natural deduction. Natural deduction is it's called that because this is presumably the way it's think. Whereas machine-oriented proof system, the main idea is who cares for human understanding? If a computer can do it fast, it's okay, right? It may be horribly complicated for a human being, but that's considered all right. You understand the point I mean, right? So, um, there must be some simpler way to do this. To make it, okay. Yeah. Okay. So the slide is changing, right? So now there were very early attempts to build theorem proofs for. So when I say this kind of machine-oriented proof systems for propositional logic or whatever logic, uh, surprisingly, it goes back to the days when computers were being built. Do you know when the first computer was built? Does anyone know? When were computers built? Which were the first computers? Yeah? Somebody tell me.
Is it abacus? Is it abacus?
I'm here.
Abacus?
Okay. Well, modern computers. I mean, then you can talk about Babbage, who tried to build the analytical agent. And then in the 20th century, with the advent of electronics, vacuum tubes, computers started being built. And when were these digital computers built? Electronic computers? Do you know? Anyone? Any guess?
70s?
Sorry?
70s?
No. Gayatri, yeah, okay. Yeah, anybody else? I want just guesses. Come on. Quickly Google search and tell me. Yeah? Okay. But yeah.
The 50s?
Huh? Sorry?
50s? The 50s, sir.
50s, yeah.
Yeah,
1950 roughly. Yeah. John von Neumann built, in the Princeton group, built a computer. In Cambridge, there is one. So von Neumann's computer was called Johnniac. There is Univac. There is ENIAC. There were, ACK for accumulator. So really old world terminology. And Fortran was, as a programming language, was designed for working on Joniac. The Princeton group, led by von Neumann, came up with a programming language, Fortran, for formula translation. Really, they were really taking math stuff and trying to plug it in. And so this is early 1950s. And in fact, I don't know how many people know that the first computer in India was built in TIFR, Tata Institute of Fundamental Research, in 1957. So India had one of the earliest computer building projects in the world. I think pretty much after the 3 US groups and Cambridge, after that I think the next one was so, but it didn't lead to major development of computers in India, unfortunately. Yeah, so my point is, and these were days before semiconductors, no transistors. So these were computers built with vacuum tubes, huge computers, filling up a whole room for, I think, the main memory of Joniac was of the order of, I don't know, some few K, right? So we're not talking about gigabytes and so on. So it's just a few hundred. So, and what I'm pointing out is that this idea that even with computers like that, right? So I'm really talking about 1950s, when they were actually building the first computers, clunky things before semiconductors, no transistors, vacuum tubes. One of the first projects was to do theorem proving in logic. So this is what I'm talking. So this idea of machine-oriented proof systems goes way. So it was clear early on that any definition of artificial intelligence should include the ability to prove theorems. And remember, Turing's paper was titled "Can a Machine Think?" This is what we launched. And so the idea of computers being intelligent predates actual first computers. In 1954, Martin Davis programmed this Jonia, this phenomenal machine, implementing Pressburger arithmetic. You don't even know what is. It's the first order arithmetical theory with addition, no multiplication, ordering, less than ordering. That's it. Zero. So it's the first order. We have talked about various arithmetical languages. This is one which has addition but no multiplication and ordering. And so this is one of the earliest projects, nothing less than Pressburger. And Martin Davis wrote. And Martin Davis says its great triumph was to prove that the sum of two even numbers is even, not even two numbers. Right? So he could use this huge, powerful computer in Princeton to actually prove that sum of two even numbers. And but 1956 in Carnegie Mellon University, Newell, Shaw, and Simon wrote a program called the Logic Theorist. And it proved the first 38 theorems of Russell-Whitehead principle. So, people were actually having this grand vision of formalizing mathematics, trying to look at formal logical theories and have computers actually prove theorems automatically. So, and these are programs written on exactly what I told you, vacuum tube machines. In the same machine, this is, Simon and Newell moved to Carnegie Mellon later on. Herbert Simon got the Nobel Prize in economics. Simon and Newell got the Turing Award for this work, and for general problem solving, all that came later. At that time, they were in Princeton and programming by John. In 1960, Davis and Putnam wrote a procedure which they called a computing procedure for quantification theory, and where they actually came up with an algorithm which could be used for the satisfiability problem for first order and how it would go. And this is very interesting. Huh? And they came up with more or less the resolution principle that I'm talking about, but not quite. And in 1962, Davis, Logeman, and Loveland came up with a machine, they call it a machine program for theorem proving, or automatic theorem proving. That was in the same. And today, these two things together, put together, is a procedure which is very popular. It's called DPLL for Davis, Putnam, Logeman, and Loveland. Really combines the two algorithms. And I'll talk about that as we go. And in 1965, John Allen Robinson wrote a paper called A Machine-Oriented Logic Based on Resolution. So all these were attempts which are about as different from whatever we have seen, Hilbert-style systems or simple calculus or as chocolate cheese. These are completely different things. Thinking afresh, like I said, the spirit of this line of work is I don't care about human understanding. I don't care about the semantic consequences, right? I don't care about that. How easy it is for a machine to do it, right? I want something simple, and I want an algorithm that I want to execute. And the machine should be able to automatically do it. That was the kind of dream. And by 1960s, there were any number of geometry theorem proving projects. People were taking up many very challenging theories to where they wanted the system to prove theorems. Yeah, and it's also interesting to note that Putnam, Robinson, these were all philosophers. John Allen Robinson is a philosopher, and Putnam is one of the famous philosophers of the 20th century. And Martin Davis is a mathematician. Later on in NYU, I don't know, he was also in Princeton. And so these people were collaborating on things, and they were looking at hard questions like what does it mean for a machine to prove? So even the field artificial intelligence did not exist as an area of research. It's just that all these people were looking at computing, looking at what is notion of truth, what is notion of proof, what does it mean for a machine to do these things, what does it mean for a machine to discover theorems. So this was the kind of ambiance in which this whole line of research took place. And as I said, it was a very fertile interaction between philosophers, programmers, mathematicians, electrical engineers. Someone like Martin Davis, he did everything. For Neumann, for instance, a great mathematician, but he worked with electrical circuits and dirtied his hands with vacuum tubes. Built things. So these people were going back and forth between all these kind of, and they were writing all these programs in Fortran. So, okay. So we're not going to go into that. I'm just telling you the history of this to point out that finally the proof principles that they came up with are dramatically different from all this. And rather interestingly, all this led in the mid-90s to the so-called SAT solvers, which are programs which, for satisfiability, Boolean satisfiability, which turned out to be very, very fast and changed technology for satisfiability. Very impressive fashion. But what is very interesting is that the SAT solvers depend directly on this line of research. So, the resolution proof system, which comes through this tradition, it's really in the extreme. There's only one rule. There are no axioms here. Right? So what kind of a proof system is this? But there is pre-processing. So pre-processing is something that programmers are very fond of. You want to solve a problem, do a lot of pre-processing, keep it ready, and then unleash the program on it. So here, the rule is exactly one. What is the rule? If you have derived alpha or beta, and if you have derived not beta or gamma, you are allowed to derive alpha or gamma. Now, this is clearly sound. Why is it sound? Forget about consequence. I'm really interested in proving valid formulas. Right? No assumptions. Even worry about that. Suppose alpha or gamma is not valid. That means what? There is a model that makes alpha false and gamma false as well. Right? Well, it makes alpha false, but this is valid, so it must make beta true. But here, if beta is true, not beta is false, gamma is also false. So how is this valid? Right? So it's not possible. So if you have ever derived alpha or beta, and if you have ever derived not beta or gamma, you can surely derive alpha. So the resolution principle is just this. Take two different disjuncts, and if there is a common formula that is occurring both positively and negatively, get rid of it. So you can reduce. Is that? So it's a kind of a reduction. So one thing it assumes is that the formula that you begin with is a whole bunch of disjuncts. Right? In fact, you can think of it as a conjunction of disjuncts. Right? So alpha or beta and not beta or gamma, in fact, implies alpha or gamma. Right? That's all it is. So basically it turns out that this is all you need, at least to prove that a formula is unsatisfying. So what is this idea? I'm not interested in valid formulas. Well, what is the negation of a valid formula? If alpha is valid, what can you say about negation of alpha?
Not satisfied.
It's unsatisfying. That's right. So the system is used for refutations rather than proofs. This is very important. Suppose I want to show that alpha is valid. I deny alpha, start with not alpha, and show that in fact it's unsatisfying. That is the idea. So, and it turns out that to show that something is unsatisfiable, this rule is all that you need. So, what we look at are resolution-based refutations. And there's a very simple iterative procedure. First thing is negate the formula to be refuted and convert it to conjunctive normal form. What is conjunctive normal form? We'll see. You know it, but if you don't, so there is a goal formula that you have, and that is to be refuted. And main idea is, so as I said, you negate it, so that you start refuting it, translate it into conjunctive normal form, and once you have conjunctive normal form, what is that normal form? You write the formula as a bunch of conjuncts. Each of the conjuncts has only disjunctions in it. And then, what is each disjunct looking like? An atomic proposition or its negation. This is all. And this is the idea of a conjunctive normal form. So, at any point of time, what are you going to have? You're going to have a whole lot of conjuncts. These conjuncts are all called clauses. When you look inside a clause, you will find something of the form not P or Q. P or not Q or on. Like it's all, literals and disjuncts. Now you can apply the resolution rule repeatedly. What is the resolution rule going to say? Pick two of these clauses. They're going to have disjunction, right? If you find the same literal occurring positively in one, negatively in the other, right? Replace the two by a single clause. Remember our rule? Pick one like this, pick one like this. In the propositional case, in conjunctive normal form, this beta is going to be actually a propositional form. It's a literal. You might have P here, not P here, or not P here. That's all. One will be positive, one will be negative. Get rid of it. Take these two clauses, replace them by a single clause here. Yeah, that's it. And now you have more clauses. Keep on applying. Now, how long do you keep doing it? Well, until you either cannot proceed or you have derived a contradiction. Well, how can you have a contradiction? Well, you have conjuncts, right? Now, this one says P, nothing else, and this one says not P. Then there are no choices there, and you have a conjunct. So, actually, what will happen? You can think of this P as P or false. This one as not P or false. Apply resolution, you will just get false. You will get the empty clause. So you keep doing that until you. So deriving a contradiction amounts to having an empty clause. You have an empty clause. What about other case? Well, you cannot proceed. That means what? You have a clause. I mean, you have all these clauses in front of you. There is nothing that's occurring positively and negatively. So therefore, you cannot apply resolution. But this is the only possible. And what we can show is that the resolution rule is complete for refutations. It means if we manage to derive a contradiction, then the formula alpha was valid. You remember, we started with the formula, negated it, and then you have arrived at a contradiction. In that case, alpha was valid. If the procedure gets stuck, that means what? You started with not alpha, keep proceeding, and you are stuck. Then what you have left here actually gives you a counter model. In fact, that negated alpha is actually satisfiable. So the given formula was not valid. And what is it? It's very easy to show that the procedure is guaranteed to terminate. So you know that you start with something, it is going to end. It's going to end either with a contradiction, in which case the originally the formula was valid, or it gets stuck, in which case the negation of the formula was satisfiable. The formula was not valid. So this is in fact a Saunders procedure. So it's amazing in its simplicity. Of course, what has gone completely is any kind of hope of human understanding. Because firstly, by the time you take the formula and translate it into conjunctive normal form, you've lost all meaning. And then you are doing this mechanical procedure of picking some things, resolving, putting it back. There's no hope of understanding that. But who cares? That's that. Is the principle clear, what we are doing? What resolution is and how it works? Any questions related to that? Yes? Okay, any questions? I'll continue. I don't want to do a proof of this. That the first part is completely straightforward. Come up with the empty clause. The formula is valid. That's very straightforward. It's just by soundness of resolution. The other one, well, if the procedure gets stuck, from that deriving a model as a counter model for alpha or a model for negation alpha. That's a little more. Now, firstly, what is this normal form? Let's get into the details. Now, if you take any propositional formula, alpha, what does it do? It defines a Boolean function. It defines a Boolean function which takes all the propositional symbols here alpha and assign it to 0 or 1. Right? This is, you understand this, right? That given any Boolean formula, any propositional formula, it defines a Boolean function. Why? Because you look at all the propositional assignments that make it true. That's precisely what. Sorry, it's raining and the water is coming in. Okay, so I hope this is clear. If it's not clear, please stop and ask. I'm waiting for questions. Nobody's asking questions. So it's okay. I'll tell you. So every propositional formula defines a Boolean function, and I hope this is clear. Now, we can think of this Boolean function as, well, let's say that there are if the propositional symbols in the formula are P1, P2, K, right? There are K propositional symbols, K Boolean variables, right? Now, then, this is a map from 0, 1 to the K to 0, 1, right? So I can think of it as a table which has got 2 power K rows for all possible assignments of truth assignments for P1 to K. So that will give you 2 power K truth assignments. And in each of them, if you evaluate the formula, it turns out to be true or false, right? So the K plus 1th column will have 0. So it's a Boolean matrix with 2 power K rows and K plus 1 columns. Now, to find the models of alpha, what do you need to do? You have to look at all the rows with the last column entry 1, right? Well, take each such row. I can write a formula corresponding to that row. What is that formula? Well, beta alpha for the rth row is the conjunction of gamma I, where gamma I is pi if the ith column entry is 1, and oh, I'm sorry, that not is yeah. It's not pi, yeah, not pi. So whatever you say, you march down that row. Okay, P1 is 1, P2 is 0, P3 is 0, P4 is 1. That means P1 and not P2 and not P3 and P4. That is the formula corresponding to that. Right? Now, what do you have to do? Then the formula alpha equals R over, look at all the rows which make it 1, right? And just write the formula beta alpha, right? Because this says that either P1 is 1, P1 and not P2 and not P3 and P4, or not P1 and P2, whatever. Good. So now it's very easy to check that these are all the models that make alpha true. So therefore, alpha is actually logically equivalent. That equality sign is also wrong. It should be equivalent. Alpha is logically equivalent to the disjunction of the formulas corresponding to the rows which have the last column entry. I've been sloppy in writing this, but I was hoping that everybody said that they knew propositional logic, so I hope you know this kind of thing. Just as a recall. All right. So, what is the important thing here? The important thing here is that I can write the formula alpha as a disjunction of conjunctions. Right? And how does each conjunct look? As a literal, either an atomic proposition or its negation. So such a thing is called, when it is a disjunction of conjunctions, you call it in disjunctive normal form. Disjunction of conjunctions where each conjunct is a literal. What's a literal? Either an atomic proposition or its negation. This is what is called disjunctive normal form. So obviously, what is conjunctive normal form? Clearly, this also gives a conjunctive normal form for negation alpha. Remember, this is what I said you wanted to do. You want to take a formula to be refuted, negate it, convert it into conjunctive normal form. Or write a formula in disjunctive normal form and then negate it. You get to a series. Yeah. So, but you can directly, of course, you don't have to go through this. Take any formula alpha. You can also directly convert it into conjunctive normal form. And for that, what should you do? Well, firstly, you must get rid of implication, right? Alpha implies beta as not alpha. Now you've got only negation, conjunction, and disjunction. Now take the formula and negation of alpha. Well, you can always push negation all the way through until it appears only in front of the formula. So now you have a formula which has only conjunctions and disjunctions. Now use distributive. Always keep pushing it, right? Use the fact that alpha and beta or gamma is the same as alpha and beta, or it's not what you want. You want alpha or beta and gamma as alpha or beta and alpha. That's it. So finally, you will get a bunch of conjunctions, each of which is conjunctions, each of which is a disjunction, and that last disjunction, each disjunction is a so the point is that for every formula, there is an equivalent formula in conjunctive normal form, disjunctive normal form. Now, of course, what about implicational normal? If you can have a conjunctive normal form, if you can have a disjunctive normal form, surely you can have an implicational normal. What would be that? Fine. You have to tell me. Pretty much. How would implicational normal form? Joe is waiting for somebody else to say something. So come on. The implicational normal form is going to look like literal L1 implies L2 implies Ln implies so. Where each literal is Lj equals P or negation. Yeah. So, as usual, negation always appears only in front of atomic propositions, and then otherwise you use only implications. So, you can write formulas in whatever normal form you like. Now, which particular normal form you want is a matter of what you want to do with it. Right? Suppose you want to show that formula is valid. Which normal, and I tell you, I'll give it to you in whichever normal form you like. I want you to check if your formula is valid. And I'll give it to you in whatever normal form you want. Which normal form would you choose? Or, yeah?
Implicational normal form.
Why?
We only need to check implications of the form true implies false. So,
True. Yeah. Yeah, this is true and that is false. Yeah. Okay. What about checking for satisfiability? Which would you like? It's a propositional formula, and you want to check if it has an assignment at all. Which normal form? So you are allowed to.
The implicational normal form always has an assignment by taking the first proposition false.
Yeah, so it's not a. Yeah. But how does that? So what you're saying is that maybe there is no. I mean, you can't have every formula equivalent to one and implication of another. That's what you're saying, right? Okay, let's forget about implication of normal form. Let's just look at only conjunctive normal form and disjunctive normal form. Okay, between conjunctive and disjunctive normal form, which would you choose? For you want to check validity, which will you choose? You want to check satisfiability, which will you choose? As I said, somebody is going to do the work and present it to you in that form.
the satisfiability disjunctive normal form.
Disjunctive normal form. Yeah, why?
As long as one of the clauses evaluates to true, we know that the entire formula is satisfiable.
Okay. And for validity, obviously it should be CNF. I mean, since you said DNF for satisfiability, it should be, yeah. But why? How would you use that? You falsify one of them. You falsify any one of them, and you know that. But okay, but this is depending on luck, right? Is there some characterization? I mean, can you say that a formula in DNF is satisfiable if and only if some particular condition that can be easily checked? Formula in CNF is valid if and only or. Yeah. So think about it. Yeah. Remember that, okay, suppose proposition occurs both positively and negatively inside one of the clauses. What does that mean for DNF, CNF, etc.? Okay, so think about it. I don't want to go further in this. Anyway, this is not part of it's not important. This is only to say that this pre-processing actually is useful, but the pre-processing is also very expensive. Very expensive in the sense that given a formula, converting it into DNF, CNF, remember I said use distributively. That will blow up the size of the formula. So you're going to have a pretty big formula on hand. And that is something to keep in mind. Okay, so let me explain how resolution works with the help of one example. So suppose you have got a formula P or Q and P implies R and Q implies R. Now we want a refutation. So we want, how do you refute this? Take the left hand side of the implication and that is true. and you want this to be false, so this and negation. So in conjunctive normal form, of course, I've chosen something so that it's very easy to write. So this is P or Q, this is not P or R, this is not Q or R, and you have another conjunct here, not R. So there are 4 clauses, this is P or Q, this is not P or R. So it's already in conjunctive normal form, and we can use it. So we have 4 clauses. The terminology is to call these things clauses. And there are 4 clauses here. I've named them 1, 2, 3, 4. Now I can resolve 1 and 2 because this is P or Q and this is not P or R. And I get Q or R, the new clause. So throw it in the 5th clause. Remember, it's not present. Now I can resolve 2 and 4 because this is not P or R and this is not R. And I get not P. And the new clause, which is not there, so clause 6. Now I resolve 3 and 4. Here is not Q or R, here is not R, and I get not Q. Now I can resolve 5 and 7. 5 and 7, I get R. And now I've got 4 which says not R, 8 which says R. I resolve the 2. Remember, this is really not R false, and this is R false. So that what you get is the empty clause. Empty clause denote the box and so we have to. Now, I was doing various things here. I was doing something completely pointless here. Step 6 here is a valid proof step, but utterly useless. So this is another thing about resolution. You pick 2 and follow, it's okay, you make progress, but it may not be actually contributing to it. So that's also part of it. So resolution just says pick 2 clauses, apply resolution, put the resolve the clause. And you keep doing that. Pick any 2, check, keep doing that. So, and in the process, you may be wasting time. That's okay. So resolution refutations are easy to implement. It's, I'm sure you can see that it's completely trivial. Write a program to take your formula, convert it into CNF, it's straightforward. Keep the clauses at any time, pick 2 clauses, resolve with this, pick 2, keep doing. It's very trivial to write a program. There are a lot of decisions to be made. At any time, there are several pairs of candidate formulas that can be resolved. Which one to try first? Right. Now, like even in this silly little example, you can either resolve these 2 or you can resolve these 1 and 3, 2 and 4, all kinds of possibilities. 3 and 4. I mean, I've of course chosen one which gives you lots of elements. And these kind of dilemmas are very important for computation because, what order do I try? The order doesn't matter. Unfortunately, it does. And I advise you to actually play around with examples and convince yourself that the order actually matters. Now, with very small, 4 clauses, 5 clauses, already you can show that order matters, but it's not that critical. But if you can come up with a family of formulas, parameterized SNN, you can very easily see that it's very easy to push one wrong choice into, completely down the wrong path. And, choosing the right clause can make a difference between getting an answer very fast and very slow. And there is a beautiful theorem by Haken. It shows that there are some simple formulas of length n whose resolution refutations require size 2 to the omega. So there is an exponential lower bound. Tell you that this can be really nasty. And the kind of formulas that you can play around with, I'll even tell you this. It's great fun to, write down propositional formulas for this and check it out. This is the pigeonhole principle. It says n plus 1 pigeons cannot be placed into n holes without a collision. So write a formula Obviously, alpha will take n as a parameter. Right? And you can write a formula of order n, which states the pigeonhole principle. And you can write it in CNF as well. It's also quite easy. And Haken's theorem will tell you that no resolution refutation exists, which is polynomial. It's at least exponential. So resolution is a very simple rule, but it comes with all this caveat that programs, the more deterministic your program is, the easier it is to control. The more choices it makes. So some heuristics are useful. Two heuristics were found to be useful, and this is what was the contribution of. And as I said, resolution was a rule proposed by John Allen Robinson in 1965, but in 1960, Davis and Putnam gave a procedure which is very close to resolution. And in fact, they even in 1962, they gave these kind of heuristics to. Davis Putnam, their way of proceeding was decide an ordering on the variables. Right? I said P, Q, R, etc. Right? Let's say the alphabetical order. That means what? First, always look for whether you can get rid of P. Then check whether you can get rid of Q. Then you get rid of R. And so on. So fix an ordering on the variables and follow that order. And then it is clear that, after all, you chose an ordering on the variables. How did you come up with it? No particular reason, right? And you could have chosen it simply wrong, and that sends you wrong. So 2 years later, Davis DLL paper came up with these heuristics, and in fact, it was precisely the heuristics, and that they showed can lead to remarkable. And but they didn't formalize it using the resolution. It's Robinson who gave it. But now it's all you can combine it. Main idea is prefer a resolution step involving any unit class. Suppose you have a class with only one literal, just says not P, Q. Right? Now, remember this is sitting inside a conjunct. That means what? Somebody has made the choice for me. Right? That means Q has to be made true. You have written not P, P has to be made false. Put that in propagated. Propagated means that somewhere else you have said that here it says P true. That one says not P or Q. Reduce it. Bring it to Q. Is that? And second is what is called the concept of support. Choose a resolution involving the negated goal or any clause derived from the negative. Remember, I had to prove something. Right? So that negated goal was R had to not. So use that to guide you. Now these are all heuristics. You already know that Haken's theorem tells you that there is lower bound. Can't do that. But these heuristics turn out to be very useful. So this is as I said, the method proposed by TLL, improving upon 60s, and it's resolution based. Now, in resolution based techniques, it's very easy to give refutation of an unsatisfiable problem, but it's not direct. I told you, when it gets stuck from what you have, you should be able to get a model of that counter model of alpha, model of negation. But that's hard. So DPLL takes the other approach. So in the DPLL algorithm, you start with the formula alpha, build a model for it. If it's actually satisfiable, it's easy to. But if it happens to be unsatisfiable, to get a refutation is difficult. So that's a choice. So resolution and DPLL represent two different viewpoints. Resolution is for refutations, showing the unsatisfiability of a formula. DPLL is for showing the satisfiability. pages. And DPLL, as I said, showed an improvement over the earlier algorithm, and they could handle something like 20, 30 propositional symbols. And that was considered very good. Well, it is very good. Right? You can handle 30 propositional symbols, because if you're going to use the truth table, you have to look at 2 power 30 vectors. Right? So instead of 2 power 30, this could really run fast. So that way it was good. By mid 1980s, there was this technology called binary decision diagrams, and BDD-based solvers could try hundreds. And then SAT solvers came along in the mid 1990s, and they could comfortably work with thousands. Now, thousands of atomic propositional symbols really means that you are considering the truth function, which looks at 2 power 1000. So that's not possible at all by exhaustive search. So all this truth table-based nonsense. So you do need these, and as I said, these are all based on the DPL. And current tools, today's SAT solvers work with hundreds of thousands of propositional symbols in a few seconds. So this is really dramatic progress, which we could not have thought of. When I was doing my PhD, we were told that if you could show something NP hard, it's nasty. Now, today, if you can do NP coding, great, because you can run a SAT solver. So no problem. So, and SAT solvers have made most of these kind of tools like child's play. Now, what is the DPLL technique? Just explain. So, what it does is that given a formula in CNF, it tries to build an assignment P such that, this is what you have to do. Given a formula, you have to find an assignment that makes it true. Now, for an assignment, I will use the sequence notation. It's just convenient to write rather than a map from variables to 0, 1. So what does the sequence P, Q bar, R mean? P is set to true, Q is set to false, and R is set to true. So it's just, this is the notation that you probably learned in school, where they have one chapter on Boolean logic in class 11. Is the kind of So I prefer to present DPLL as a state transition system, because this is the kind of language that's easy for me. But you can write pseudocode programs. So states are of the form where V is a partial assignment and alpha is a formula. And remember, when you use resolution, you take those clauses and put new clauses. So you keep changing it. The way I will illustrate it, you don't have to change anything. But that's how the actual DPLL is. So states are of the form. States carry two inputs. One is the partial assignment that you have, and the current clause is the formula and clause form. And the initial state is, of course, empty because there is no assignment, and you are given the formula. Transitions, you have transition relations, which is with the current assignment, I move to the new assignment. I take some action on that new assignment. And in the process, I may change the formula. And so there are 4 kind of transition rules. There are 2 transition rules for extending the current assignment, and 2 transition rules for repairing or updating the current, because I may have made some wrong choices. So for extension, there are 2 principal actions. One is decision, and the other is unit propagation. What is the decision rule? Well, look at the assignment, and let's say P is undecided so far. It's a partial map, right? So initially you start with the empty assignment. So at any point of time, you are looking at V where some variables have been assigned, some have not been assigned. If P is undecided so far and occurs at all, don't care, positively or negatively, somewhere, well, decide. And how do I decide? I move to new where V is extended by P, and I call this, I put a mark D, saying that this is a variable I have decided to be true. Yeah. And I'm not changing it. And then there is unit propagation. Unit propagation says, from a state where you have got assignment V, I go to a new state where I extend it with P. And what do I see? Well, if P is occurring as a clause, that's it. P is a unit occurring. And alpha contains a disjunct, beta or P. And the current valuation V does not satisfy beta. Now, if suppose you had a unit clause where P was occurring with nothing else, think of this as false or P. And V, of course, does not satisfy. So this will certainly. Yeah? But in general, now I have got an undecided. I know that P must be made true because I've got a clause saying beta or P, right? And beta is not true. At least I can check, right? Under my current assignment, beta is false, so therefore P must be made true. So I extend. So these rules help us to extend the current partial model and assignment. Are the two rules clear? The two rules are, one is, if there is a proposition that has been so far undecided, it's occurring somewhere, make a choice. The second thing says that if a proposition P is, forced on you, it's forced on me because I'm asserting beta or P, and beta is not true under the current assignment, so P must be made. So extend P. And then you have two repairing. What does repairing means? I made a choice, right? Remember, my decision, I just guessed something. I wrote P, right? The deciding. Maybe that was wrong. And as I go down, I find out that it doesn't work. So what do I do? So there are two so-called repairing actions. One is fail and the other is what is fail? Fail means I am in the state where I have come up with a partial assignment, and then I go ahead and I find that there is an entire disjunct beta, and B does not satisfy beta, and I don't have any decision proposition. Right? That means maybe I started with unit propagation, kept on making decisions, and I have arrived at a disjunct that is false. Simply fail. In this case, you announce fail and stop. And well, what is the other possibility? There is backtrack, where I have a decision proposition. What does that mean? I go through my assignment. This is a sequence. Somewhere in between, there is a P occurring, which is a decision. I have made a decision P. And now I find that the current assignment does not satisfy beta. Right? It's the same situation here. My current assignment is not satisfying beta. But in this particular case, there is no decision proposition. Therefore, I fail. Here, I look at the decision proposition. I have decided P, and that has led to this failure. So I go to a new state where I backtrack. Right? Backtrack means what? That decision for P, I change it into P bar. Right? I had made an, by the way, I'm using notation. Yeah. The way I decided was the decision was always positive, and I changed it into a negative decision. And V prime contains no decision propositions. What does this mean? Look at the new vector. Here I started with V, a decision variable, and then V prime. In the new state, I've thrown away this entire. What does this mean? Because all the V prime here, all those decisions were dependent on P, the decision I had made. The moment I change this, all this may be wrong. So this is the idea of backtracking. I'm going down a tree. I keep deciding. I decide for X, then I decide for Y, then I decide for Z, and I find a problem. Now I go back, change that. Whatever is in the history, That's okay. But anything that came afterwards, I just put ID star. So this is the notion of backtracking. And so basically, whenever you encounter a problem due to an earlier decision, if there is a decision that you can reverse, you go and reverse. Keep doing that. At some point, all your decisions will be removed. And if at that point you fail, you fail because there is no option. In fact, the formula is not satisfied. So let me show a couple of examples. So here are clauses. It's P bar or Q. I mean, there's no meaning. It's just some cooked up stuff. So I start with the empty clause, and I have to decide something, and I decide P. Okay? And then now I do unit propagation. Because P is something that I have decided, and I see the effect of P. So this is already P bar or Q. Right? But P has been said to be true. So Q has to be 1. So I'm not writing QD here because this is not a decision I made. Right? This is forced on me. So by unit propagation, I extend it to PDQ. Now, then I decide. I look here, is there anything that is forced? Nothing that is forced. I could have actually checked it. Well, even here, nothing is forced. So no variable is decided by that. So I make a new decision, R. And I'm implicitly following the ordering PQR. Just need to follow something. And and I record the fact that R is a decision. And now I walk down. Remember, there is unit propagation possible now. That will give me S. Unit propagation. And now again I look. Is any of these decisions going to give me anything? Nothing. So I make a decision and I decide T. Okay. And now I can see whether there is a unit propagation possible. Yes, it is. Unit propagation is U bar. Okay. So this is the vector I've got. P is positive. All of these are positive. U is negative. And there are 3 decision points here. Now, look at the last disjunct. It says Q bar or T bar or U. This is false because Q is true, T is true, and U is false under the current assignment. So I need to backtrack. So what do I backtrack to? I backtrack to this decision T and I go to T bar. Right? Because now T has to be some true false. Do that. And I continue. Now I can again, sorry, this was it should be U. Yeah, this is not, the last one is not T, but U. That's a decision. Because U is not forced anywhere. In fact, U is bar. Q, T bar. So, I'm sorry, this is unit propagation and that will give me U. By unit propagation, I get U. And in fact, we are done because we've got a complete assignment. And nothing is falsified. No more to do. Sorry about the last step. So that last one is. Yeah. And so now we see, well, this is a decision because I've got T bar that doesn't say. This also doesn't say. And nothing is forced. So I have to decide and I decide. So it's a decision step. Any questions about this example? Okay. So this is how DPLL works. We take one more example. In this example, what I have done is here is a clause with 3 literals, and here is a unit clause. And then this is all possible things you can say for Q. Either this or and this or this. So Q bar, so if you look at it, all the 4 possibilities. So you can imagine that. So with Q and R, there is no decision possible. You have to depend on these. And look at what happens. Well, start with the empty one. And right now I can do unit propagation because P is there. Right? I don't have to decide anything. There is a unit clause. Must be made true. Now, what about Q? Nothing is forced based on P. So I make a decision, PQ. Now I can do unit propagation. This will give me R. So I have fixed PQR. But the moment I fix Q and R, I'm going to get this disjunct, which will fail. Yeah. So this disjunct is false. So backtrack. What do I backtrack to? I change Q to Q bar. Well, the moment I do Q bar, I can do unit propagation. This will give me R. Right? So I've got PQ bar now. But now this clause is going to fail. This one is going to fail. And now when this fails, what is the problem? One of the regions is false. I can't go back and change anything because there is no decision to backtracking is not going to help. There is no decision to undo. So I'm done. I'm failed. This is the user. So this example is to illustrate how fail happens. So as it happens, of course, that is a problem. So, and you can check that, obviously you can't have any assignment that is going to make these concepts true. Of course, it's not something. So, I mean, I'm again doing this to only illustrate how DPLL works. I mean, these both resolution and DPLL, correctness is completely straight. Right? You just make the observations about properties. It gives a decision procedure for satisfiability. First thing, you should be able to convince yourself that there are no infinite sequences starting from the initial state. Why? At every step, your assignment keeps increasing. Well, it also decreases, but can it keep oscillating? Well, anytime when I go back, I have removed a decision variable. Right? And the number of decision variables is bounded. There are n variables, there are only n decision variables. The moment you undo a decision, you never make a decision on that again. So, how many backtracking steps are possible? N minus 1. That's it. So that ensures that there are no infinite sequences. So that means that every path in the transition system is finite. Well, then what does it end with? If the latter is a final state, means I can't proceed at all from there, all variables have been assigned, then it's easy to show that alpha is in fact satisfiable and V satisfies alpha. How do you prove this? Take such a path, do a proof by induction on the length of the path, show that your partial assignment is always a model. Therefore, at any point of time, the assignment is a model along the path, and therefore the last one is that's a complete assignment. On the other hand, you could end with a fail, but then you have to do the exam satisfied. This is a little bit of work. This is a little bit of work because you have to argue that this is what I said in resolution, showing that it's a refutation is very straightforward. In the cases where it gets stuck, that it terminates, right? Not to do contradiction, to show that what you call the quantum model. Here, this one takes a bit. You have to show that alpha is unsatisfiable, not very difficult. You prove the converse. Suppose alpha were satisfiable, there would have been an assignment possible. Use that assignment to say that this guy would have had a backtracking possibility and would not have. That's all. So, this is basically all this, as I said, was to show you how, sort of mathematical logic for computer science. This is computer science. And this is really engineering, what you might call logical engineering. Modern SAT solvers are DPLL based, but use many more heuristics. They use what is called conflict-driven clause learning. What you do is you build an implication graph as you go on. An implication graph says that if I said this, I must say that. Not so much about true and false. It just says if any decision on this will force a decision. And you keep doing that, and whenever there is a conflict, you find a cut in the implication graph that led to the conflict. And then you derive a new clause with a negated assignment, exactly as we did. And then this is a very interesting innovation they introduced in the 90s. Now, DPLL, when it wants to backtrack, what does it do? If you remember, if you take the assignment, take the last decision clause. Right? Remember that the tail after that has no decision at all. Take the very last decision variable and flip it. So chronologically it backtracks. And this is the logical thinking. Now, like I said, I've forgotten now what that program is called, 96, where they said, forget chronological backtrack. You non-chronologically backtrack. You say a conflict arose with P. Even if P was decided long ago, you go back all the way, undo P, and get rid of everything following. So, in DPLL, at any point of time, you look in the vector, look at the last possible decision, and do that. Here, you go back all the way, and for whatever reason you have decided, you throw away all this. It looks like, you would think that this will generate much more work because you're throwing away longer. It turns out that this was a dramatic improvement. Okay, so as I said, SAT solvers now is mainly an engineering discipline. There are all kinds of improvements. People keep conferences, competitions, a lot of very clever people trying out things. I don't understand much of what's happening in SAT solvers, but what is very impressive is the technology. Like I said, these people can look at benchmarks. The exponential lower bound remains. By the way, Hawkins' lower bound remains for DPL. You can very easily show that the pigeonhole principle for n will drive the SAT solver to prove that it's exponential. No problem. So lower bound still remains, but somehow these things work very fast, and like I said, they can work with literally hundreds of thousands. Now, in the remaining time, I will just introduce this notion of first order resolution. Not going to do much details of that, but so for propositional proof systems, we're pretty much done. What? Hilbert proof system argues that it's complete. We have the natural deduction, secret calculus. I didn't prove cut elimination, but I argued that it's also complete by showing that all the Hilbert rules can be derived in these, and all these rules can be derived in the Hilbert system, so they are equally powerful. And then the resolution. Now, what is interesting is that the Davis-Putnam procedure and Robinson's resolution rules were introduced not for propositional logic, they were for quantified logic. In fact, I told you the title of the paper. It's a machine-oriented proof for quantified formulas. So resolution is very simple. And Robinson, a machine-oriented resolution system. And so he builds this entire thing for first order logic. It's really beautiful, a single rule for first order logic. And so it's very simple after all. You're saying alpha or beta, not beta or gamma. You derive alpha or gamma, get rid of beta. That sounds very good. But what about variables? There are free variables floating around. Okay? So how does one handle variables? And that's all that. That's so Robinson's point is that if you know what to do with the variables, resolution is natural. So suppose you have for all x, px implies qx, and you have p of c. Now we could substitute c for x. You will get the clauses. This is not p or q, so you will get not p or q and p, and you can resolve p not p and get q. You can apply proposition. The problem is, how do you find substitutions? So the key is finding correct substitutions, and that is the entire thing. So for the rest of the discussion, fix some first order language. Assume some fixed constant symbols, function symbols, predicate symbols. So some vocabulary. Now, in general, what is a substitution? A substitution, we are going to take variables and we want to substitute them by terms. That's what we do. Right? We take a substitution is a partial map from variables to term for some variable. But it's partial function. The same variable is not mapped to different terms. Each variable is mapped, but some variables you will decide. Yeah. So that's what is substitution. Now, well, customarily you write it as a set of pairs. You say x is mapped to this term, y is mapped to this term, t prime, and so on. Notice that when I say x is mapped to t, y may occur in t. And when I say y is mapped to t prime, x may occur in t. So all this is possible. And x may be mapped to a term which contains x. And that is possible. It's just a substitution. And we use theta prime. Now, if theta is a substitution, it's a map on variables. Right? I can lift it to a map on terms. But of course, the lifting should be done very carefully. Right? When you lift, people say, no, be careful. Because remember, the image of theta contains variables. Right? Suppose I map x to f of y and y to g of x. Right? You should be careful because simultaneously everywhere wherever x occurs, you are replacing with g, y. And wherever y occurs, you are replacing by f of x. Right? So all this should be done simultaneously. You can't do it in order because everything will change. You have to do it carefully. But it's trivial to mathematically define this. I'm just saying operationally for those who do it by hand. So now we have this very nice notion. And we have two terms T1 and T2. We say they are unifiable if there exists a common substitution that makes them identical. That's all. Very simple idea. If two terms, I can find a common substitution that makes them identical. Then I say that the two terms are unifiable. Is the idea clear? So, in resolution, what is the problem? I have alpha or beta, negation beta or gamma. I want to get alpha. But this is not propositional. Beta is going to come with some variables. This negation beta is going to come. If I can find some substitution such that after applying the substitution, this is actually beta, this is actually not beta, with all the things correctly, then I can. This is the idea. So unifiability is at the heart of this. So in this case, theta is said to be a unifier of T1. Let me take some examples. Suppose T1 is x and T2 is y. Then xy is a unifier, as also yx, right? Because this term is x, that term is y. I just have to rename. Now, for this, there is another very simple unifier. X is mapped to C, y is mapped to C. That also means under the substitution comes out. Much more complicated unifier is x is mapped to f of z, y is mapped to f of g of c, and z is mapped to g of c. You can check that it also comes out. What will you get? You will get f of g of c here, and you will get f of g. So unifiers can be very complicated. And you're just saying two terms are unifiable, there exists such a substitution. From unifiability, you have a notion of most general unifier. And this is really very simple, very elegant. Now, if I give you two substitutions, you can compose them. Right? This maps x to some term. Look inside, the second substitution says, first substitution says x is mapped to t. Second substitution says x to t prime. Look inside t wherever x to t prime. So you will get a new. So these are maps that compose. In general, we say that if you give me two terms t1 and t2, I say theta is the most general unifier. If you take any unifiers t1 and theta1, remember that there are lots of possible unifiers. I can always find a substitution theta2 such that the effect of theta1 and t on t1 is the same as theta2 of theta of t1. And T2 is the same as. So basically what you are saying is a most general unifier is a unifier such that every unifier factors through this. So in some sense, I've got T1 and T2. There are lots and lots of possible unifiers. I find the most general unifier to be one such that you find any other unifier, I can always find a substitution that gives me. So it is in this sense the most general. So if I take two, I said it for terms, now you can generalize it for any expressions, in particular for atomic formulas, for any formulas. If I take P of x and P of c, the most general unifier possible is x is assigned c, x substituted by c. This is true. Suppose I have got P of f of x, y, g of x, and I've got f of x, x, g of x. What is the most general unifier possible? Well, here y has to get x has to get y. Right? So either you can write the pair x is mapped to y or y is mapped to x. So even though it's called the most general, it's not unique. What we can do is to show that it's unique up to rename, up to publication. So in general, people say the most general unifier, but that's wrong because it's just a maximal one. But all the maximal ones are identical up to relay, up to permutations. Now, what about this? If I have got P of G of f of v, G of u, P of xx, right? Now, this says that x should be mapped to G of u, right? But this says that x should be mapped to G of f of v. But that's easy. I just have to map u to f of v. That's all. So x is mapped to G of f of v, u is mapped to f of v. So that's in fact the most general. What about MGU of Pxfx and Pxx? Well, because here this says that a function symbol must occur in this. So MGU in general need not exist. But there is a very simple, and Robinson's paper, what he did was to show that there is an algorithm which given any two checks if MGU exists, and if it exists, finds it. Once you have that, you can now represent the generalization of the resolution. That's it. The familiar one, except that where there is a most general unifier, if you can find the most general unifier theta, which makes these two identical, then you can get rid of them. Everything else is identical. Of course, you have to have conjunctive normal form for pseudo logic also. I didn't presented that, but I will show you. And so you do all that. So bring out all the quantifiers to the left, column normal form. And then you have the propositional part, bring it to conjunctive normal form. So I don't have time to do these examples. And, and resolution forms the inference engine for logic programming languages like Prolog. Let me skip this. It's not important. So the main idea is that you can treat logic as a programming language. Write formulas in clausal form and let the underlying inference engine run. So your program only specifies relationships between boards and underlying machine figures out. So it's a kind of automatic program. This became very popular in the 1990s. The Japanese invested a lot of money in what they call fifth generation computing systems. But all that is now passing. Today, machine learning has taken over as the paradigm. So logic-based paradigms. But this was only to tell you that this line of research has actually led to very important developments in computer science. And this, I'm just not going to get back to this, but to tell you that there is a way of looking at all these things, which is entirely implementation algorithm oriented. And by just pursuing that, people have come up, ignored lower bounds, come up with amazing technology, something that's immensely practical and useful, like in the case of the TPLL procedure and such. And so this is a foray that, as I said, we'll get back to our and we have to look at how do you do Hilbert-style proof system for quantifiers, sequent calculus, what are the kind of rules for quantifiers. We'll take a